Hello, today we will discuss about the topic image histogram. First, what is meant by histogram? A histogram is a graph that shows the frequency of anything. Usually, a histogram have bars that represent the frequency of occurring of a data in the whole data set. A histogram has two axes, the x-axis and the y-axis. The x-axis contains event whose frequency you have to count, and the y-axis contains the frequency. The different heights of bar shows the different frequency of occurrence of data. The basic tool that is used in designing point operations on a digital images or any other operation as well is the image histogram. The histogram HF of the digital image, F is the plot or a graph of a frequency of occurrence of each gray level in F. Hence, h of f is a one-dimensional function with domain 0 to k minus 1. A second possible range extending from 0 to the number of pixels in the image m into n. The histogram is given implicitly by h of fk is equal to j. It is also denoted by h of rk is equal to nk, where rk is the kth intensity value and nk is the number of pixels in the image with the intensity rk. Here, the histogram is also denoted or implicitly by h of fk is equal to j. If f contains exactly j occurrence of gray level for each k is equal to 0 to up to k minus 1. Thus, an algorithm to compute the image histogram involves a simple counting of gray levels, which can be accomplished even as the image is scanned. And the histogram of the digital image with the intensity levels in the range 0 to L minus 1 is a discrete function of, it is also represented in terms of h of rk is equal to nk, where rk is the kth value or kth intensity value and nk is the number of pixels in image with the intensity rk. It is common practice to normalize a histogram by dividing each of its components by the total number of pixels in the image, denoted by the product of m into n, whereas usual m and n are the row and the column dimensions of the image. Thus, the normalized histogram is given by P of rk is equal to nk upon m into n for k is equal to 0, 1, 2 up to L minus 1, where P of rk is an estimate of the probability of occurrence of an intensity level rk in an image. The sum of all the components of a normalized histogram is equal to 1. The histogram are the basis for numerous spatial domain processing techniques. The histogram manipulation can be used for image enhancement. In addition to providing the useful image statistics, we shall see in a subsequent that the information inherent in histogram also in a quite useful in other image processing applications, such as it is also useful in image compression and in image segmentation. The histogram are the simple to calculate in software and also lend themselves to economic hardware implementation, thus making them a popular tool for real-time image processing. Then, what is the histogram of an image? Histogram of an image, like other histogram, also shows the frequency, but an image histogram shows the frequency of pixel intensity values. In an histogram, the x-axis shows the gray level intensity and the y-axis shows the frequency of this intensity. For example, the figure is the for histogram of an image. We draw the histogram for the above pictures of the Einstein would be something like this. This figure shows the histogram of the above figures. The x-axis of the histogram shows the range of the pixel value. Since it's an 8 bpp image. That means it has a 256 levels of the gray or the shades of gray in it. That's why the range of x-axis starts from the 0 and ends at 255 with a gap of 50, whereas on y-axis is the count of these intensities. This figure shows the four basic image types that are dark, light, low contrast, high contrast, and their corresponding histograms. The right side of the figure shows the histogram corresponding to these images. The horizontal axis of each histogram plot correspond to intensity values Rk. The vertical axis correspond to the values of h of Rk is equal to Nk or P of Rk is equal to Nk upon m into n. If the values are normalized, thus the histogram may be viewed graphically simply as plot of h of Rk is equal to Nk versus Rk, or P of Rk is equal to Nk upon m into n versus Rk. We note in the dark image that the components of the histogram are concentrated on the low dark side of the intensity scale. Similarly, the component of the histogram of the light image are biased towards the high side of the scale. An image with a low contrast has a narrow histogram located typically towards the middle of the intensity scale. For a monochrome image, this implies a dull, washed-out gray look. Finally, we see that the components of the histogram in the high contrast image cover a wide range of intensity scale and the further that the distribution of pixels is not too far from the uniform, with a very few vertical lines being much higher than the others. It is reasonable to conclude that the image whose pixels tends to occupy the entire range of possible intensity level and in addition tend to be distributed uniformly will have an appearance of high contrast and will exhibit a large variety of gray tones. The net effect will be an image shows that a great deal of the gray level details and has high dynamic range. It will be shown shortly that it is possible to develop a transformation function that can automatically achieve this effect based only on information available in the histogram of the input image. Then our next topic is application of histogram. In digital image processing, histograms are used for simple calculations in software. It is used to analyze an image. Properties of an image can be predicted by the detailed study of the histogram. The brightness of the image can be adjusted by having the details of its histogram. Next one is the contrast of the image can be adjusted according to the need by having details of x-axis of a histogram. It is used for image equalization. Gray level intensities are expanded along the x-axis to produce a high contrast image. Then our next topic is histogram equalization. Histogram equalization is a common technique for enhancing the appearance of the image. Suppose we have an image which is predominantly dark, then its histogram would be skewed towards the lower end of the grayscale and all the image details are compressed into the dark end of the histogram. If we could stretch out the gray levels at the dark end to produce a more uniformly distributed histogram, then the image would become much clearer. Consider for a moment continuous intensity values and let the variables R denote the intensities of an image to be processed. As usual, we assume that R is in range from 0 to L minus 1 with R is equal to 0 representing the black and R is equal to L minus 1 representing the white. For R satisfying these conditions, we focus attention on transformation intensity mapping of the form S is equal to TR, where R is lies from 0 to L minus 1. Let us we are considering the again a range of R from 0 to 1 with R is equal to 0 representing the black and r is equal to 1 representing the height. The transformation function is of the form s is equal to t of r, where r is sliced from 0 to 1. It produces a levels for every pixel value r in the original image. This figure shows the monotonically increasing the function, showing how the multiple values can map on a single value. The figure is showing a monotonically, and figure B is showing straightly the monotonically increase the function. This is a 1-to-1 mapping both the ways. Let us consider S is equal to T of R, that is R is sliced from 0 to L minus 1, that produce an output intensity level S for every pixel in the input image having intensity R. We assume that T of R is a monotonically increasing function in the interval 0 to lies between 0 to L minus 1, that is R is sliced from 0 to L minus 1, and B represent 0 to 0 less than is equal to TR less than is equal to L minus 1, that is R is realized from 0 to L minus 1. In some formulation to be discussed later, we use the inverse, that is R is equal to T inverse of S, while S is sliced from 0 to L minus 1. The requirement in condition A that T of R be monotonically increasing guarantees that the output intensity values will never be less than corresponding input value, thus preventing the artifacts created by reversal of intensity. Condition B guarantees that the range of output intensity is the same as the input. Finally, the condition A dash guarantees that the mapping from S back to R will be 1-to-1, thus preventing the ambiguities. Figure shows a function that satisfies condition, that is A and B. It satisfies both the condition, that is A and B. Here we see that it is possible for multiple values to map to a single value and still satisfy these two conditions. That is, a monotonic transformation function performs a 1-to-1 or many-to-1 mapping. This is perfectly fine when mapping from R to S. However, the figure A presents a problem if we wanted to recover the values of R uniquely from the map values. That is, the inverse mapping can be visualized by reversing the direction of the arrow. This would be possible for the inverse mapping of SK in figure A, but the inverse mapping of SQ is a range of values which of course prevent us in a general form recovering the original values of R that result in SQ as shown in figure B. Requiring that T of R be strictly monotonical guarantees that the inverse mapping will be single value, that is, a mapping is 1-to-1 in both directions. This is a theoretical requirement that allows us to derive some important histogram processing techniques later in this chapter, because in practice we deal with the integer intensity values. We are forced to round all the results to their nearest integer values. Therefore, when strict monotonicity is not satisfied, we address the problem of non-unique inverse transformation by looking for the closest integer matches. The intensity level in an image may be viewed as random variables in the interval, that is 0 to L minus 1. A fundamental descriptor of a random variable is its probability density function, that is a PDF. PDF nothing but the probability density function. Let PRR and PSS denote the PDFs of, that is a probability density function of R and S respectively, where the subscripts of on P are used to indicate that PR and PS are different function in general. A fundamental result from basic probability theory is that if PR of R and TR are known and TR is continuous and differentiable over the range of values of interest, then PDF of transform variables, that is a probability density function of a transform variable S, can be obtained by the simple formula, that is PSS is equal to PRR magnitude of dr upon ds. Thus, we say that the PDF of output intensity variables, that is S, is determined by the PDF of the intensity values and the transformation function used, that are R and S. A transformation function of a particular important or particular importance in image processing has in the form of, that is S is equal to T of R is equal to L minus 1, that is infinity, or that is integration from 0 to T PR of omega dw. This is the cumulative distribution of function of R, where omega is a dummy variable of integration. The right side of the equation is recognized as the cumulative distribution function, that is a CDF of random variable R, because PDFs means probability distribution function, always are positive, and recalling that the integral of the function is the area under the function. It allows that the transformation function of an equation of above equation is satisfy the condition A, because the area under the function cannot decrease as R increases. When the upper limit is in this equation is R is equal to L minus 1, the integral evaluates to 1. The area under the probability distribution function curve always is 1, and so the maximum value of S is L minus 1. Here L is the total number of possible gray levels in the image. To find the PSS corresponding to the transformation, we use the equation we know from Leibniz rule in basic calculus that the derivative of a definite integral with respect to its upper limit is the integrand evaluated at the limit, that is ds upon dr is equal to derivative of t of r in terms of dr with respect to dr, that is the derivative of s with respect to dr is equal to derivative of tr with respect to, that is derivative of s with respect to r is equal to derivative of t of r with respect to dr is equal to L minus 1 derivative of d of dr, then integration of 0 to t pr w dw or omega dw, that is L minus 1 is nothing but pr of r, that is a derivative and integration are reciprocal to each other, therefore cancel each other, therefore we get L minus 1 pr of r function. Substituting this result for dr upon ds in equation 1, keeping in mind that all the probability values are positive and else, that is PSS is equal to PRR magnitude of dr upon ds, therefore is equal to pr upon r 1 upon L minus 1 PRR is equal to, we get 1 upon L minus 1, that is s is sliced from 0 to L minus 1, that is the value of s is sliced from 0 to L minus 1. We recognize the form of PSS in the last line of this equation as a uniform probability density function. Simply stated, we have demonstrated that performing the intensity transformation in equation yields a random variable S characterized by a uniform PDF. It is important to note from this equation that T of R depends on PRR, but the equation shows that resulting PSS always is uniform, independently of the form of PRR. This figure illustrates the concept of an arbitrary PDF and the result applying the transformation into all the intensity levels are the resulting intensity S have a uniform PDF independently of the form of RS. To fix the ideas, consider the following simple example. Suppose that the continuous intensity values in an image have the PDF, that is probability density function, that is PRR is equal to lies in between, that is 2r upon L minus 1 square is for r is lies between from 0 to L minus 1 and 0 is for otherwise. From equation we have already discussed above S is equal to T of R is equal to L minus 1 integration 0 to R P R W dW is equal to 2 upon L minus 1, that is integration 0 to R omega dW or W dW is equal to R square upon L minus 1. Suppose next that we form a new image with the intensities S of 10 using this transformation, that is the S values are formed by squaring the corresponding intensity values of the input image and dividing them by L minus 1. For example, consider an image in which L is equal to 10 and suppose that pixel in an arbitrary location x, y in the input image has an intensity R is equal to 3. Then the pixel in that location in the new image is S is equal to T of R is equal to R square upon 9 is equal to 1. We can verify that the PDF of the intensity, that is a probability distribution function of the intensity in the new image, is uniform simply by substituting PRR values in above equation. So using the fact that S is equal to R square upon L minus 1, that is PSS is equal to PRR magnitude of dr upon ds is equal to 2r upon L minus 1 bracket square magnitude of ds upon dr with taking a reciprocal or inverse of dr upon ds. 2r upon L minus 1 bracket square, that is a derivative of R square upon L minus 1 with respect to dr is equal to 2r upon L minus 1 bracket square magnitude of L minus 1 upon 2r. That is derivative of R square is 2r and L1 minus 1 is constant because we are taking the derivative of R with respect to R. Therefore, R square according to the formula x raised to n, that is equal to n x raised to n minus 1. Therefore, R square is equal to 2R. L minus 1 term is cancelled, 2R term is cancelled, we get 1 upon L minus 1. Where the last step follows from the fact that R is non-negative and we assume that L is greater than 1. As expected, the result is a uniform PDF. For discrete values, we deal with the probabilities, histogram values and summation instead of probability density function and integral. As mentioned earlier, the probability of occurrence of an intensity level R of k in a digital image is approximated by Rk is equal to nk upon m into n, where k is from 0, 1, 2, dash dash up to L minus 1, where m into n is the total number of pixels in the image and n of k is the number of pixels that have the intensity R of k and L is the number of possible intensity levels in the image. For example, 256 for 8-bit image. As noted in the beginning of this topic, a plot of PR of Rk versus Rk is commonly referred to as a histogram. The discrete form of the equation is S of k is equal to T of R is equal to, or T of Rk is equal to L minus 1 integration 0 to T PRW dW is S of k, T of Rk is equal to L minus 1 summation of j is equal to 0 to k PRRJ is nothing but PRRJ is represented in the form of nj. Therefore, L minus 1 upon mn summation of j is equal to 0 to k nj, where the k is values lies from 0 to up to L minus 1, that is 1 to dash 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 up to L minus 1. Thus, the proceed output image is obtained by mapping each pixel in the input image with the intensity R of k into a corresponding pixel with the label Sk in the output image. As by using the above equation, the transformation mapping T of Rk in the equation is called as a histogram equalization or histogram linearization transformation. It is not difficult to show that these transformations satisfy the A and B we already stated in previous of this section. This figure represents the transformation function for histogram equalization transformation. 1 through 4 we are often from the histogram of the images from top to bottom in the left column by using the equation S of k is equal to T of Rk L minus 1 summation of j is equal to 0 to k PR R of j. Let us considering the histogram equalization example. Let us considering the table that shows the intensity distribution and the histogram values for a 3-bit 64 by 64 digital image. Here for R0 is equal to 0, NK is equal to 790. We are considering the values of R up to 7. Therefore, H0 is equal to T of R0 is equal to 7. Summation of J is equal to 0 to 0. PR R of J is equal to 7. PR R0 is equal to 1.33. Similarly, we can find the values for S1 is equal to T of R1. T of R1 that is 8 minus 1 that is L minus 1. Therefore, 8 minus 1 summation of J is equal to 0 to 1. PR Rj is equal to 7 PR R0 plus 7 P1 R1. Therefore, we are substituting the value of R0 and R1. We are getting the value 3.08. Similarly, we can find for all the R values that is from 0 to 7. We get S0, S1, S2, S3, S4, S5, S6 and S7 values. By using these values, we can draw the histogram as shown in a graph A, that is PDF, that is probability distribution function. Histogram equalization of 3 8-bit image. The figure A shows the original histogram, figure B shows the transformation function, and figure C shows the equalized histogram. By using the formula Sk is equal to T of Rk L minus 1 summation of J is equal to 0 to K P R Rj. By using this formula, we can find the values of S0, S1, S2, S3, S4, S5, S6 and S7, and we draw the histogram diagram for these values. By using the formula, we get the value of S0 is 1.33. We are considering its rounding of nearly to 1. S1 is equal to 3.08. Therefore, we are considering the value of S1 is 3. S2 is equal to 4.45, rounding off to 5. S3 is equal to 5.67, rounding near to 7 and rounding near to 6. S4 is equal to 6.23, rounding near up to the 6. S5 is equal to 6.65, rounding nearly to 7. S6 is equal to 6.86, rounding nearly to 7. S7 is equal to 7 is we are considering the 7 value. This all the values of equalized histogram. Observe that there are only the 5 distinct intensity level because R0 is equal to 0 was mapped to S0 is equal to 1. There are 790 pixels in the histogram equalized image with these values. The table showing the values of these images. Also, there are in this image 1023 pixel with the value of S1 is equal to 3 and 850 pixel with the value of S2 is equal to 5. However, both the R3 and R4 were mapped to the same values 6. So there are 656 plus 326 that is 985 pixel in the equalized image with these values. Similarly, there are 245 plus 122 plus 81 that is 448 pixel with the values of 7 in the histogram equalized image. Dividing these numbers by Mn is equal to 4096 yielded the equalized histogram as shown in figure C. Because of a histogram is an approximation to a PDF that is probability distribution function and no new allowed in the intensity levels are created in the process. Perfectly flat histogram are rare in a practical application of histogram equalization. Thus, unlike its continuous counterpart, it cannot be proved in general that discrete histogram equalization result in a uniform histogram. However, as you will see shortly, using the equation has the general tendency to spread the histogram of the input image so that the intensity levels of the equalized image span a wider range of the intensity scale. The net result is a contrast enhancement. This figure shows the histogram equalization. The left column of figure shows the 4 images and the center column shows the result of performing the histogram equalization on each this image. The first three results from the top to bottom shows the significant improvement. As expected, histogram equalization did not have much effect on the fourth image because the intensities of this image is already span the full intensity scale. The third column in figure shows the histogram of the equalized images. It is of the interest to note that while all these histograms are different, the histogram equalized images themselves are visually very similar. This is not unexpected because the basic difference between the images on the left column is one of the contrast, not content. In the other word, because the images have the same content, the increase in contrast resulting from the histogram equalization was enough to render any intensity differences in the equalized images visually indistinguishable given the significant contrast between the original images. This example illustrates the power of histogram equalization as an adaptive contrast enhancement tool. The next one is what are the advantages of histogram equalization. This method is usually increase the overall contrast of many images, especially when the usable data of the image is represented by close contrast value. This adjustment allows the intensity to be distributed better on the histogram. This allows the area of lower contrast to gain the higher contrast. This is all about the histogram equalizations. So today we are going to study the image histogram and image equalizations. Thank you so much.